value of GYY is a solution to classical equations of motion, right? Because as long as GYY is constant, and this is 0 and this is say eta mu nu, it's a constant metric, so Riemann tensor is 0, and hence it's automatically a solution to equations of motion, right? So GYY you can easily conclude that it's a modulus field, okay? Because constant GYY doesn't change, producing the curvature in the background.
So what was the definition of a modulus field?
That a field which has no potential, okay, which basically means that you can write down a solution where the field is an arbitrary constant, right, in flat metric, and that will be a solution to the equations of motion. Right? So here, even before writing the action involving these fields, right, in which case of course you should be able to check that it has no potential, but even before writing the action, we know that a constant GYY, right, will always be a solution to the equations of motion, right, because it produces flat metric. So it will be a modulus field. Okay, so these are the three fields that you get from a metric, and then from C3 you get C3 mu nu rho, which is a free form, and C3 y mu nu. So this is a two form. This is going to be a two form in 9 plus 1 dimension. And if you now recall the field content of type 2A supergravity, okay, you will recognize that this field content is exactly the same as what we had in type 2A supergravity. Of course, we had the metric in type 2 supergravity. We had a two form, right? The B2 mu nu, right? So that B2 mu nu, we have a two form here. Okay. We had a dilaton, a scalar. We have a scalar here. And then from the Ramon sector, we had a one form and a three form. Right? So this is a one form, a vector field, okay, and this is a three form. Okay, so the bosonic field content is exactly the same as what we had in type 2 supergravity. Okay. In fact, it's also not hard to see that the fermionic field content will be the same. Okay. So what is the fermionic field content? So we begin with psi mu hat, which is the 11-dimensional spinor, right? Because in 11 dimensions there is a gravity law. Okay. Now a spinor in 11 dimension, because there is no chirality, okay, is 32 dimensional. Okay. So a spinor, a 32 dimensional spinor in 11 dimensions splits up into two Majorana-Weil spinors in 10 dimensions. Okay. So furthermore, this mu hat again splits into mu and y. Okay. So psi mu, this will represent two Majorana-Weil spinors in 10 dimensions, okay, for each mu. Okay. Furthermore, because in 11 dimensions there is no chirality, okay, these two Majorana-Weil spinors that you get in 9 plus 1 dimensions will have opposite chirality, okay, because it is descending from 11 dimensional spinor, okay, where you cannot define chirality. Okay. So this gives you two, for each mu, two Majorana-Weil spinors of opposite chirality. That's exactly the gravity laws we had seen in type 2 supergravity. Okay. And then we have psi y, okay, again two Majorana-Weil spinors of opposite chirality. Those are the two dilatinos that we had seen in type 2 supergravity. Okay. So both the bosonic and the fermionic field contents are the same. Okay. And in fact, with some work, one can show that the actions are the same. Okay. But that will require some work, because to show that the two actions are the same, okay, we have to know how these fields are related to the fields that we saw in the type 2A supergravity. Okay. Now, at the level of linearized analysis, okay, we know what they are. Right? For example, C3y mu nu must be B mu nu, B2 mu nu, okay, at the linearized level. But then there can be corrections. Okay, we are trying to compare the full actions on the two sides. Okay, we have to know how exactly the fields are related to each other. Okay, and that becomes difficult if you use dimensional reduction in this form. Okay, so now I will describe a way to define the lower dimensional fields, which makes the job a little easier. Okay, the way we define the fields in the lower dimensions. Is this okay? Okay, so let me begin by writing down how we, starting from a metric G mu hat nu hat, how we define the fields in 10 dimensions, okay, 9 plus 1 dimensions. So the G mu hat nu hat, dx mu hat, dx mu hat, okay, so this is a total metric. Okay, this is what I'll call ds square. And now the way we'll introduce the fields in 10 dimensions is the following. Okay. I'll write this as G tilde mu nu dx mu plus G tilde mn dym plus am mu dx mu dym plus am mu. Okay, so the fields, independent fields that we will be taking, are G tilde mu nu, am mu, and G tilde am. Okay. So these are the definitions. Okay, by definition, you find G tilde mu nu, G tilde mn, and am mu by comparing these two metrics. What does that mean? That means, for example, that G mu nu will be G tilde mu nu plus G tilde mn am mu. G mn is just G tilde m, and G m mu, which is also the same as G mu m, is G tilde m n a m mu. So to linearize the order, okay, this is quadratic as you can see. Okay, to linearize the order, G mu nu is the same as G tilde mu nu. Okay, but what we have done here is that we have added some quadratic piece in defining and relating the 4-dimensional metric or 10-dimensional metric to 11-dimensional metric. Okay. Now mn here, I have kept things a little general. Okay. When you are actually going from 11 to 10, of course, mn run over only one values. Then mn are the internal coordinates. If you remember, let me remind you the definition. Okay. Our coordinates are x mu and ym. Okay. X mu runs from 0 to d, and this runs from d plus 1 to whatever it is, 11 in this case, or 10. Okay, for string theory it should have been 9. For 11-dimensional supergravity, ym goes from d plus 1 to 10. Okay, that's a general convention. Okay. For circle compactification, m takes only one value. Is this definition clear? So you have not changed the number of fields. Okay. From the metric we are supposed to get a tensor, which is here g tilde mu nu. We are supposed to get a vector am mu. Okay, m takes only one value if m is just y, and we are supposed to get a scalar which is gmn, g tilde mn. Okay, g tilde yy in this case. Okay, so it's the same number of fields, it's just a different way of parameterizing. Okay. Now I'll explain why we parameterize it this way. So to see what is the advantage of this parameterization, we need to study the general coordinate transformations, right? The effect of general coordinate transformations on these fields. Now, when you talk about general coordinate transformation, because we have taken everything to be independent of y, the y coordinates, right, the compact coordinates, we will also make a coordinate transformation that is independent of the compact coordinates. Right? Otherwise, of course, it will not preserve the property that things are independent of the compact coordinates. Okay? So, you will make coordinate transformations, but it will be independent of the compact coordinates. So, there are two kinds of coordinate transformation that you can take. One is ym, going to ym plus some function fm of x. Okay, notice that I have transformed by something which is, but the transformation parameter depends only on x. This is one class. The other class is x mu goes to some arbitrary function. Let's call it xi mu of x. Okay, these are independent transformations, right? And you can ask, how do these various fields transform under this transformation? So let's start with this. Okay, no change in x, ym goes to ym plus fmx and substitute it here. So under this transformation, the metric becomes g tilde mu nu dx mu plus g tilde mn dym plus del mu fm plus dx mu plus a mu dx mu times dyn plus del mu. So this is the change in the metric. Okay, if you make this coordinate transformation, ym we have changed to ym plus fm. And now we want to try to redefine our fields so that it can be written back in this form. And you can see that the net effect is essentially that am mu goes over to am mu plus del mu fm. No other field changes. G tilde mu nu goes to G tilde mu nu and G tilde mn goes to G tilde mn. Yes, because the only change is effectively that you are adding a del mu fm to am mu.
So why is there no effect of this xi?
No, I am not only considering this one. I will take two transformations independently. These are independent transformations, right? So first I am studying the effect of this. Then I will study the effect of this. Is this clear? So what this says is that if we parameterize our fields in this way, okay, and we can apply it to general situation, what our immediate application will be in 11 dimensional supergravity. Okay, so the key observation in all this essentially is that if we assign to AMU the usual Gauge transformation laws, okay, and the usual transformations of a vector, then this quantity is invariant under both these transformations. Okay, because under the general coordinate transformation this index is contracted, so it behaves nicely. Under a general coordinate transformation that involves shift of y, okay, as long as you shift this like a Gauge transformation, again this quantity, this combination remains invariant. Okay. So this combination is useful, okay, and that's what we are going to make use of now when we describe how to decompose a form field, okay, in lower dimensional forms. So decomposition okay. And I'll illustrate this with the three form, but it's more general. Okay, you will know, you will see immediately what the generalization is. Okay. So let's start with C3. Okay, this is what you want to understand how to decompose. Okay. So in 11 dimensions, this C3 is 1/6 C3 mu hat rho hat dx mu hat with dx mu hat with dx rho hat. Okay. And the earlier quick way of decomposing that we had described, we have just simply taken C mu rho, C m mu rho, C mn mu, and C mn p. Right? Those will be the fields. Okay, but that's not what we will do now. What we will do now is to decompose this in terms of waste products of dx mu's and the product of this combination. Okay. Instead of taking the waste product of dy m with dx mu, we will take the waste product of dx mu with this combination. Okay. Which makes no difference at the linearized level because this is already one part of the field. Right? So at the linearized level, you can just ignore this compared to this. Okay. But it will make a difference at the non-linear level. Okay. How we relate that fields in 11 dimension to fields in 10 dimensions. So let's do this. So this is 1/6. I'll write this as C3 mu rho. Let me call it tilde. These are the lower dimensional fields. Dx mu with dx mu with dx rho plus half C3 tilde. Okay, let me call it C2 tilde m mu rho dy m plus am dx mu dx rho. Okay, it's still a component of C3, but I am calling it C tilde 2 because as far as the non-compact space-time is concerned, it may be like a 2 form. Right? M is part of the compact direction. Then there will be C tilde 1 mn rho dy m plus am mu dx mu plus am dx mu dx rho. And finally, C tilde 0 mn P dym plus x mu plus a dx mu dyp plus ap dx. Okay, so this is the way we'll define our lower dimensional fields. If it's a circle compactification, then of course these two things don't exist, right? Because this is totally antisymmetric in M and N. So if there's only one index, then this is identically 0, this is also identically 0. But this is more general, okay, for a general product of circle compactification.
Will you explain the normalization, half 1 and 1 in particular?
Oh, these normalizations are basically the, okay, I can put a half factor here. It's just a, okay, normalization is really doesn't matter. I put a normalization of half here because this is antisymmetric in nu and rho, right? So there will be two terms which are equal. Right? That's the factor of half. So let's see, if you remember, we had introduced a B2 form, for example, as half B mu nu dx mu is dx rho, dx mu, right? A 3 form as 1 over 3 factorial, right? So it's that factor over here, right? So what I can do is I can put an extra half here because there are two things which are identical. Okay. So we'll give a half, but that will only normalize the definition of C's.
Then the last term also.
Yeah, last term is number 1/6.
So this transformation in y, this ym going to ym plus fmx,
Yes.
we can make it more general for more special spaces, right? In which we have general isometries. But this fmx can be a function of y in the isometry direction.
Look, the point is that the way you are doing a dimension reduction, right, for circle compactification at least, you are taking everything to be independent of the y direction, right? Now, okay. So now if you take this transformation, right, ym going to ym plus some function of y, then it doesn't preserve that property, right? So you are going out of that space in which you have restricted our fields.
Not talking about maybe not circle, but if you have general spaces in
Yeah, so in general spaces you have to find out what the isometries are and you have to use those.
those isometries could be functions of y, right?
Could be, yes, in general, right? If it's for example a sphere, right, you have to use appropriate isometric transformations, which will be functions of the spherical coordinates, but very specific functions, not arbitrary functions of the spherical coordinates, right? Here the isometries are just constants, right? I mean you are just making y translation, that's what you are gauging. Okay, that's why this transformation system. We'll come back to the general space maybe later. Okay, now the way I have introduced this, it's easy to check, and I'll give it an exercise, that if we consider this transformation, say x mu goes to this di mu of x, under this, C tilde M's transform as tensors. Okay, this will transform as tensor of rank 3. This will transform as tensor of rank 2, this will transform as tensor of rank 1, and this is a scalar. Okay, it's not hard to see, right? Because this one, these pick up, for example, del rho x mu, or del mu prime x mu times dx mu prime, right? So effectively, it will multiply C tilde 3 by the appropriate factors of derivatives of psi. This one is invariant. Right? So this one will get contribution only because this picks up factors, right? And that will transform the tensor of rank 2 and so on. It's also easy to see that if you consider ym going to ym plus fm of x, then all the C tilde m's are invariant. Because this combination remains invariant. Right? These are of course invariant anyway, right? And this combination has been chosen precisely so that it remains invariant once you make an appropriate transformation on the A mu. Right? A mu transformation we have already given. Right? That is enough to make this, keep this as it is. Okay? And as a result, there is no need to change these C tildes. Okay? These remain invariant. Is this clear? What is non-trivial, however, is the transformation under the gauge transformation of the form fields. Okay, so let's recall how the form fields transform. So there is a gauge transformation which is delta C3 equal to d lambda 2. Well, lambda 2 is a 2 form. Okay. What is lambda 2? Lambda 2 is half lambda 2 mu hat dx mu hat by dx mu hat. Okay, so you can write this as half lambda tilde 2 mu dx mu plus dx mu plus lambda tilde 2 m mu dym plus, okay, again we take it to be that form am this is actually lambda tilde 1 because as far as the lower dimensional space is concerned, it's transforming as a 1 form, and half lambda tilde 0 mn dym plus am dx 0 is dym plus am dx 0. So this was the original transformation in 11 dimensions, right, or whatever dimensions you are starting with. Okay. And what you have to do now is you have to substitute this here and see how the various components of C3 transform. Okay, so you have to calculate delta C3 by substituting this form of lambda 2, okay, and try to reinterpret this as changes in these. Is that clear? Okay, because the transformation is given already in 11 dimension, right? You cannot change C3. Okay, and you have to reinterpret this as changes in the C tildes. Now the change in C3, C tilde 3, okay, we have to pick up the coefficients of dx mu h dx mu h dx rho. Okay. So one of course comes from here, but there is another term which is coming from here, right? So when you compare, you will find that delta of C tilde 3 can be written as d lambda tilde 2 lambda tilde 2 plus lambda tilde 1 m with f2 m. So what is f2? f2 m mu nu is basically del mu am nu minus del mu. Okay, so that's coming from this term over here. We can anticipate as in rho and mu, okay, because it's waste product anyway, so with some additional factors of half, and basically that gives you this term lambda tilde 1m with f2m. And there could be other terms coming from here, okay, but that we will not worry about now. Is this clear? And you recognize this as some kind of Chern-Simons terms, anomalous transformation laws of C tilde 3. Right? Naively, you would have expected delta C tilde 3 should only involve this. Okay? But we see that it will automatically generate this additional term, even though the original 11-dimensional theory didn't have any such anomalous transformation laws. Now, one could ask, could we have avoided it? Okay, how could we have avoided it? Imagine that we expanded this. Why did we use this? Right? Why not just use dym or dx nu? You could have tried that. Okay. Then this term wouldn't contribute. Right? The unwanted term that we are getting will not contribute. Okay. But then what would happen is that we will not get this combination over here. Okay, we will only get dym. Okay. But now when you try to compare this with this side, see here the expansion involves this combination, right? If you had a independent dym with something, right, we have to first rewrite this in terms of this minus mu with something, right? So you'll again get an anomalous transformation in a slightly different form. Okay. Now it will involve an a with d lambda, okay, instead of this. Okay, so we cannot avoid an additional Chern-Simons like terms by not including this combination. Okay, it will come in a slightly different form, but it will come in here. Is this okay? Now we are in business to compare it to the type 2 string theory. So in 2a string theory, we had G mu nu, we had B2 mu nu, we had 5, and we had C1 nu, and we had C3 mu nu. Okay. G mu nu we might expect should be related to G tilde mu nu that we got in M theory or from 11 supergravity. Okay. It is not quite the same. Okay, because there will be some scaling. Okay, and we will later on describe what the scaling is. Phi we may expect should be related to GYY. Okay, that's the only scalar that we had on. Okay. Again, we have to do some work to figure out what the correct exact relation is. But phi will be some function of GYY. There is not much freedom there. Okay. Similarly, G mu nu will be G tilde mu nu up to some overall function of phi, okay, or overall function of Gy of the scalar. B2, let's see what B2 transforms. Okay, B2 is a tensor, okay, and the transformation law of B2 is just d lambda 1, lambda bar 1, we call it lambda bar 1. This you can identify, I erased that C2, this you can identify as what you have called C tilde 2 M mu nu. Okay, M takes only value y, because C tilde 2 in fact doesn't have an anomalous transformation law. Okay, you can see that the only anomalous transformation law is in the triple product dx rho dx mu dx nu. Okay, so C tilde 2 will transform nicely exactly as this one. C1, what is C1? C1 is a gauge field, right? The transformation of C1, delta C1 was d lambda 0. Okay, so do you have some such a field in 11 dimensional supergravity when you compactify a circle? That's the A mu. This one, A mu takes only one value, right? A mu transforms like a gauge field, right? No anomalous transformation in the A mu, right? So A mu you have to identify. So C1 we have to identify with A mu. This came from the metric. And finally C3. Okay, type 2b had a C3. So let me write this delta C3. So delta C3 in type 2a. Let me remind you, had the following structure. It transformed as d lambda 2 plus lambda 0 h3. This doesn't look quite alright, right? Because this is lambda 1 wedge F2, right? Not lambda 0 wedge H3. Okay? But recall that we introduced also a C3 prime. Okay, we said that we could either use C3 or C3 prime. C3 prime and C3 are related by some appropriate shift, right? So C3 prime, let me remind you again the definition. So C3 prime was C3 plus C1 OH B2. So delta C3 prime is delta C3 plus delta C1 OH B2 plus C1 OH delta B2. So delta C3, let's pick from here. So this was d lambda 2 plus lambda 0 H3 plus delta C1 was d lambda 1, so d lambda 0 OH B2 plus C1 HD lambda 1. Okay. Now this we can write as d of lambda 0 b2 minus lambda 0 times db2. Okay, the Weiss product is not relevant because this is after all a 0 form, right? d0 b2 is nothing but h3. So this cancels this. This one we can write as d of c1 with number 1, I think there's a minus sign, plus dc1 with number 1. So these two cancel. This one, d of lambda 0 b2, I can just redefine in the definition of lambda 2. Right? It's after all, lambda 2 is arbitrary 2 form, right? This is also a d of 2 form. Similarly, this one, d of this, I can absorb into the definition of lambda 2. That's some different parameter. What I left with is d of something plus dc1 with lambda bar 1. This is precisely f2. Right? And because f2 is a 2 form, I can also write this lambda bar 1 by f2. Okay, which is exactly what we have here. So this shows that to identify the type 2A fields with the supergravity fields, and 11 dimensional supergravity fields, C3 of type 2A is not the C tilde 3 that we have introduced, but it's the C prime 3 of type 2A that we should identify as the C tilde 3. Is this clear? Okay, so by doing the analysis this way, right, by defining the lower dimensional fields in the way I have done, we can ensure that the gauge transformation laws, okay, are not free from anomalies. Okay, no, they have some anomalous pieces, but the anomalous pieces are well understood. Okay, what they are. Okay. And then once you have that knowledge, you can compare it with some other known theory and see if you can match the fields. Okay. Now it's a general result, okay, that when the form fields are present in, say, higher dimensional theory, okay, then once you do this dimensional reduction, okay, you cannot make everything non-anomalous. Okay, you can transfer the anomalous transformations from one to the other. Right? Here, for example, every type to a string metric. Okay. So what this is saying is that the 11, let me call it G11 mu nu is e to the power minus 2 phi by 3 G mu nu. Okay. So this is to a string metric. And it's also saying that G11 YY is e to the 4 phi by 3. Okay, so this gives the precise relation between the dilaton of type 2A string theory and the metric, the YY component of the 11 dimensional metric. Okay, and once you make this choice, other relations I have already said what it is. You can show that the 11 dimensional action directly reduces to the 10 dimensional type 2A supergravity action. Any questions? Okay, so this of course is just an observation. Okay, nobody can contest it. You can just calculate, start with 11-dimensional supergravity action and you can reduce to 2S supergravity. Okay. But this leads to or has led to a conjecture.
One thing,
Yes.
this fact that you started with 11-dimensional supergravity and got type 2A, I mean, this generically it is I mean, true for other dimensions also. I mean, if I start with, I suppose one can define supergravity in other dimensions also.
Yes.
And then if we
Yeah, the point is if you do a dimensional reduction, right, as we argued that the number of supersymmetries is the same, right. So if you start with supergravity in certain dimensions, you will automatically get a supergravity in lower dimensions, right. Sometimes the supergravity that you get may not be unique, right, and then you may ask about which particular supergravity you get. In this case, because the number of supersymmetries is large, basically supersymmetry fixes the action uniquely. Okay, so there is no really choice for this, that it had to reduce to type 2 supergravity. Given the existence of the 11-dimensional supergravity and the 10-dimensional type 2 supergravity, right, there is no other option because both are unique, right? And we know that starting from 11 dimensions, if we just do this dimensional reduction, you better get supergravity in 10 dimensions.
So uniqueness is special in 10 and 11.
Exactly, yeah. Uniqueness is special when there are so many supersymmetries. It's also true in 4. In 4 dimensions, if you use 32 supercharges, right, which is n equal to 8 supergravity in 4 dimensions. Okay, so the conjecture, okay, which doesn't necessarily follow from this, but it's consistent with this, that if we take type 2 supergravity and take the limit that phi goes to infinity, okay, then these effectively behave like 11-dimensional theory with 11-dimensional Lorentz invariance. You see that when the 11th dimension is compact, you don't see the 11 dimensions, right? You only see 10 dimensions. So then it's a 10-dimensional theory. But this theory, in one particular limit, behaves genuinely like 11-dimensional theory, right? That's the limit when GYY goes to infinity. Okay, if at the level of the supergravity, if you just take GYY to infinity, it should, you came from 11 dimensions, right? It goes back to 11 dimensions. But the claim is that a type 2A supergravity, a type 2A string theory, okay, which is a genuinely 10-dimensional theory, that's how you formulate it. Okay. If we take the limit of phi goes to infinity, okay, that follows from this relation, then it becomes 11-dimensional theory with 11-dimensional Lorentz invariance, and that low energy theory is 11-dimensional supergravity. Is this
strong?
pardon?
That is in strong.
Yeah. So that, first of all, that's not in manifest contradiction with anything that we know, because phi goes to infinity is the strong coupling limit of type 2A. Right? If this had happened at the weak coupling limit of type 2A, then obviously nobody will believe you. Right? Because you started with a 10-dimensional theory, how can you get to 11 dimensions?
So you are saying we can see this in the 10-dimensional framework itself.
That's the conjecture. We cannot see it. Because to see it, you have to do this 10-dimensional theory at strong coupling. Right? Conjecture is that if you could solve this 10-dimensional theory at strong coupling, you will see that theory effectively becomes 11-dimensional.
But given that everything depends only in this 10-dimensional space and time directions,
Yes.
how would I recover, I mean, in a genuinely 11-dimensional theory, things can depend on this 11-dimensional.
Yes. So the point is, so let's try to see how will you see the 11 dimensions, right? Now, here we are working in momentum space. Okay, the way we went from 11 to 10 dimensions is that we made a Fourier decomposition, right? And then you see that in the Fourier modes, you can ignore the higher Fourier modes because they are heavy. Okay, so what has to happen? So the signature of the 11 dimension, okay, large 11 dimensions, is that there will be lots of nearly massless particles, right? Because in the limit when the 11 dimension, the radius of the 11 dimension goes to infinity, right? All those heavy particles, but apparently heavy particles which you had thrown away, start becoming light. Okay, so if this has to happen, okay, if type 2 super string theory has to become 11-dimensional theory in the strong coupling limit, okay, what has to happen is that you should get lots of extra massless particles or nearly massless particles in that limit. Right? Okay, that's the only way you can see, you say that you have an 11-dimensional theory, right? Because 11-dimensional theory of course has generally those particles.
Just to clarify, when you are going to 11 dimension, it still doesn't mean that you get the full set of diffeomorphisms in 11 dimension, right?
Well, that's a conjecture that you will get full set of diffeomorphisms in 11 dimension, strictly in the phi goes to infinity limit. Right? For any finite phi, of course that is broken. Right? Well, the diffeomorphism, local diffeomorphism is not broken. Yeah, so you should get the full gauge symmetry as to the 11 dimension. Right? But the Lorentz invariance you restore only in the strictly infinite radius limit. Right? 11 dimensional Lorentz invariance. Okay? But it's always good to talk in terms of spectrum. Right? Don't think in terms of the symmetries, because the symmetries appear only in the infinite radius limit. But the spectrum you can examine even for finite radius, right? For finite but large radius, you know what the spectrum should contain, right? It should contain lots of nearly massless particles of very fixed mass, right? Whose spacing is given by n over r, right? And r, we know how it's related to phi, right? It's this relation. Okay. So that's the conjecture. Type 2A string theory in this limit should appear all these light particles, which will effectively tell us that the theory is 11 dimensional. Is this statement clear?
So if one says that we are getting, we should be getting more number of massless particles, then perhaps in this particular limit of large phi, maybe things, I mean, look a little believable in some sense, but it's like we are generating one more dimension, space-time dimension, right?
Yes.
So how do I see it?
See, that's what I'm saying. That you shouldn't think of as generating space-time dimensions, because in string theory gives you the spectrum,
Yes.
right? So look at the spectrum,
Mhm.
right? Because after all, if the spectrum contains this Kaluza-Klein modes, then it's indistinguishable from having an extra dimension, right? So after all, you sense the extra dimension by probes, right?
Right.
So as long as the Fourier modes are all there,
Mhm.
right? If you have this infinite number of particles at equal spacing,
Mhm.
right, given by 1 over r, then it's as good as saying that you have an extra dimension.
Mhm.
Okay, but it has to happen for every particle that you have in the system, right? Because everything is coming from the Fourier modes, right? We only keep the zero Fourier mode,
Mhm.
right? So all the higher Fourier modes must appear
Mhm.
for every particle.
So, so shouldn't we say that there really were 11 dimensions and we are looking at 10 dimensions, and then we are recovering the same thing by looking at a particular limit of the
Yes, except that we don't have a fundamental formulation of the 11-dimensional theory, right? Whereas we do have at least a perturbative formulation of type 2 string theory.
Oh, good question. Like,
Yes.
if you say that the full set of symmetries is restored, that means the spectrum also should become continuous.
Yes, exactly. So because that will automatically happen, right? If the spectrum goes as n over r, right, and r is given by the so r basically is e to the 2 phi by 3, right, square root of gy. Right? If spectrum goes as n over r, and if phi is going to infinity,
Okay,
right, then it is becoming continuous, right?
But how do you check this in supergravity, that whether spectrum is being continuous or not?
Yes. In supergravity there is no way you can check it, because supergravity you have thrown away all those modes, right? Okay. But in string theory there is a hope to check it. Okay. So because string theory is not supergravity, right? String theory contains other particles.
But to check this, don't you need a non-perturbative definition where we do strong coupling statement?
Yes.
Strong
So the
coupling?
point is that it turns out there is a way to check this. Okay. It has not been completely settled, but I'll tell you what is the way you go about checking it. Okay. So we have to first ask what are these extra particles, right? The particles which carry momentum in these extra dimensions. Okay. Particles which carry momentum in these extra dimensions are charged under the gauge field that comes from gravity. Right? That's the standard Kaluza-Klein mechanism, right? Because G m mu, right, or what I have been calling A m mu, right? A mu, that is that, so all the particle carrying momentum in these directions, okay, are charged under that field, okay, which means this n over r, okay, should represent the charge of that gauge field mu, Okay. Now, what is the gauge field mu in type 2 string theory? We have identified it, right? It's a one form field that comes from Ramon center. Okay. So, what are the particles that are charged under that one form field? D0 brane, right? So, D0 brane is what is charged under that one form field. Okay. So, a particle carrying unit momentum we already have. It's the D0 brane.
And that's non-perturbative.
Yeah, because it's BPS, so it's non-perturbative all the way. Okay. What this conjecture tells us, okay, that besides the D0 brane, single D0 brane, okay, you should have bound states of arbitrary number of D0 branes. Imagine that you had an n D0 brane bound state, which is also a stable particle. Okay. Then it will provide you automatically these calcium modes. It carries charge n over r, right? N units. A single D0 brane corresponds to a single mode of the calcium, a single unit of momentum. Okay. So what this tells us that if this conjecture has to hold, okay, then type 2 string theory must contain not only single D0 branes but bound states of n D0 branes for arbitrary n.
Is that non-trivial statement, or I mean, because for D3 branes we typically consider stack of.
Well, you can consider stack of D3 brane, but they are not necessarily bound. That's a non-trivial statement, right? That there is actually a bound state. Okay. Here the difficulty is that the bound state of take 2 D0 brane, right? The bound state of 2 D0 brane has exactly twice the mass of single D0 branes. Okay. It should have, because the mass we have seen is n over r, right? Okay. So, 2 particles of mass 1 over r is the same as a particle carrying 2 units of momentum. So, at the level of supergravity, supergravity, (2a) on S1 is 2b on S1. Okay, and I'll write down the relationship. So G2a YY is some constant over G2b YY. K is arbitrary. And e to the minus 2 phi 2a square root of determinant G2a is the same as e to the minus 2 phi 2b. And this is supposed to be exact a true symmetry. This is at the level of string theory again for k equal to 1. Okay. This is the alpha prime equal to 1. Okay. So first of all, when I say that these two are equivalent at the level of the supergravity action, when you do this dimensional reduction in the same way I told you, right, you get 8 plus 1 dimensional theories on both sides, right? So the dependence on the y, and you will see that supergravities are identical with this identification, and then the form fields also get identified appropriately. Okay. You can first of all check that the counting works exactly as it should, okay. And then the map between the two you can figure out by looking at the gauge transformation also. Okay, just like we did for the theory and type 2 supergravity. Now, this looks a little strange again, because take for example type 2b, right, and take gyy goes to 0. That's the limit when the circle size is becoming very, very small. But from type 2a perspective, gyy goes to infinity. So you grow an extra dimension, right, where you would have naively expected that you lose one dimension, right? You should go back to you should go to your theory should become closer and closer to 9-dimensional theory, right? But in the extreme limit, it becomes 10-dimensional theory, right? Because this goes to infinity. It's similar to what happened there. Here, in fact, there is another strange thing. If you just look at it, right? You see that here the relationship between phi 2a and phi 2b are such that for fixed values of these determinants. Well, I think actually I can just write for circle compactification. I don't even need the determinants. Okay, so this is, I'll write it as G G2a yy, and this is G 2b yy. Okay. Okay, so the second strange thing is that in the weak coupling limit of this theory, you also reach the weak coupling limit of this theory. Okay? Because weak coupling limit corresponds to phi goes to minus infinity. Okay? Because G is e to the phi, right? So phi goes to minus infinity weak coupling limit. So as you take phi 2b to minus infinity, phi 2a also goes to minus infinity. Okay? So here you cannot say that this is a strong coupling phenomenon, right? This is happening at weak coupling. Nevertheless, somehow, when the circle size here is going to 0, okay, instead of becoming more and more like a 9-dimensional theory, it's becoming again like a 10-dimensional theory. Okay. So one can again ask, okay, that this time that you have weak coupling on both sides, we could stay at weak coupling on both sides. We should be able to now verify this. Okay, it's either true or false, right? But you cannot invoke strong coupling string theory to say that we don't know how things work. So exactly in the same spirit as we had earlier, the growth of an extra dimension means that you have extra states, extra light states, right? Because you have a 1 over r, right? Imagine that this is going to 0, so this is going to infinity. Okay, so you should have lots of extra light states. Okay. But on this side, the circle size is going to 0. Okay. So clearly, characteristic line modes are not responsible for it. Okay, so the extra light states, if they exist, must come from somewhere else. Okay. It turns out that those extra light states essentially come from the string winding modes along the circle. Okay. So let's imagine that this is the circle size R2a. As R2a is going to 0, the characteristic line modes are becoming heavier and heavier. But strings which are wound along these circles, they are becoming lighter and lighter. Right? Because a string wound along this circle will have the mass proportional to the length of the circle. Okay. So they become lighter and lighter, and they start behaving like characteristic line modes. Okay, they are behaving as far as the spectra and interactions are concerned. Okay. They are behaving exactly like that of a characteristic line mode. Okay. And that's the way we actually establish this duality. Okay. So even though you take r goes to 0 limit here, okay, effectively you grow a dimension because the string winding modes now start behaving like characteristic line modes. So this is again one of the stringy magics, right? In the ordinary geometry you will never see this. Right? If your usual notion of geometry holds, right, then if the circle size becomes smaller and smaller, then the theory should look more and more like an 8-dimensional theory or 8 plus 1 dimensional theory. It happens here up to the point when the circle size goes to square root of alpha prime. But beyond that, it effectively becomes larger and larger dimension. Okay, so maybe I'll stop here and then next time I'll finish whatever is left about circle compactifications, and then we'll start with Calabi-Yau. So next week there will be no lectures. It will start again the week after.